Ever looked up at the night sky and wondered how it all began? How our tiny blue dot Earth came to be, nestled in this vast, cosmic ocean? The answer, surprisingly, might not lie with our own planet, but with the colossal king of our solar system, Jupiter. Today, we're diving deep into the origin story of this gas giant, a tale that could rewrite everything we thought we knew about our cosmic home. Imagine the early solar system, over 4.5 billion years ago. It's not the orderly place we see today. It's a chaotic, swirling disk of gas and dust called the solar nebula, orbiting a young, fiery sun. Out of this primordial chaos, planets began to form. And one of the biggest questions in planetary science is, who was first? For a long time, the leading theory was a model called core accretion. Think of it like building a snowman. You start with a small, icy rock, maybe 10 times the mass of Earth. This core rolls through the nebula, and its gravity starts pulling in more and more material. Dust, ice, and eventually, vast amounts of hydrogen and helium gas pile on, layer by layer. Over millions of years, this snowballing effect builds a giant planet. In this story, Jupiter is the big brother, forming slowly but surely, taking its time to grow into the behemoth we know today. This model is elegant, and it explains a lot. It tells us why Jupiter has a dense core and a massive, gassy atmosphere. It seems to make perfect sense. But there's a problem. A big one. Time. The early solar system was a dangerous place. The young sun was blasting out intense solar winds, powerful enough to blow away all the light gases, like hydrogen and helium. If Jupiter's core took too long to form, we're talking millions of years, its potential atmospheric fuel would have been long gone before it had a chance to grab it. The clock was ticking. So, how could Jupiter have grown so massive, so quickly? This puzzle led scientists to a more dramatic, more radical idea. Disk instability. Forget the slow, patient snowman. Picture a cosmic flash flood. In this scenario, the solar nebula itself wasn't perfectly smooth. It had dense, unstable regions. In one of these regions, gravity suddenly took over, causing a massive clump of gas and dust to collapse in on itself, all at once. Whoosh. In just a few thousand years, a mere blink of an eye, in cosmic terms a gas giant is born, fully formed. This model solves the time problem beautifully. Jupiter could have formed rapidly, capturing its immense atmosphere before the sun had a chance to blow it all away. So, we have two competing origin stories. The slow, methodical builder versus the fast, chaotic collapse. Core accretion versus disk instability. Which one is right? For decades, this was one of the fiercest debates in astronomy. But the clues to solving this mystery are hidden inside Jupiter itself. And thanks to NASA's Juno spacecraft, we're finally starting to read them. When Juno arrived at Jupiter in 2016, it started mapping the planet's gravitational and magnetic fields with incredible precision. Scientists expected to find a small, solid, well-defined core, just like the core accretion model predicted. But what Juno found was weird. Jupiter's core isn't small and compact. It's big, fuzzy, and diluted, spread out over nearly half the planet's radius. It's a mix of heavy elements and hydrogen, not a neat little ball of rock and ice. This was a bombshell. A fuzzy core doesn't fit neatly into either of our simple models. A slow-growing core should be dense. A fast collapse shouldn't even have a distinct core. So, what happened? The evidence suggests something even more violent and complex than we imagined. Perhaps Jupiter's birth was a multi-stage process. One new and exciting theory is that Jupiter's fuzzy core is the result of a cataclysmic collision. Imagine a young Jupiter, just finished forming, when it gets slammed by another massive planet, a protoplanet maybe 10 times the mass of Earth. This giant impact would have been powerful enough to shatter Jupiter's original, compact core, scattering its contents and mixing them with the deep atmosphere. It's a violent, chaotic birth that would explain the strange, diluted core we see today. It combines elements of both theories. A core forms, and then a dramatic, instability-like event changes everything. So, why does any of this matter for us, here on Earth? Because Jupiter's story is our story. The timing of its birth had profound consequences for the entire solar system. Let's explore one scenario. If Jupiter formed very early and very quickly, as the disk instability or giant impact theories suggest, it would have acted like a cosmic bouncer. Its immense gravity would have carved a huge gap in the solar nebula, effectively creating a barrier. This barrier would have prevented material from the outer solar system from drifting inwards. This is crucial. The inner solar system, where Earth formed, was hot and dry. The outer solar system was cold and full of icy bodies, comets, and asteroids rich in water. By forming a barrier, an early Jupiter might have starved the inner planets of this water-rich material. So how did Earth get its oceans? Perhaps through a later scattering of comets, nudged our way by Jupiter's gravitational influence long after the initial formation period. Now let's consider the other possibility, the Grand Tack hypothesis, which fits with a slightly later formation. In this model, Jupiter forms and then begins to migrate inwards, tacking through the solar system like a sailboat. It moves as close to the Sun as Mars is today, scattering the small rocky planetesimals in its path. This inward journey helps explain why Mars is so small. Jupiter may have gobbled up or thrown out much of the material that would have otherwise formed a larger Mars. Then Saturn, forming a bit later, also starts to migrate inward. When it gets close enough, it gets locked in a gravitational dance with Jupiter. This powerful duo then reverses course, migrating back out to their current orbits. As they moved, their gravity would have acted like a giant cosmic snowplow, flinging icy asteroids and comets from the outer solar system into the inner solar system. These water-rich bodies would have then rained down on a young, dry Earth, delivering the very water that fills our oceans and flows in our veins. In this story, Jupiter is not a bouncer, but a delivery service for the ingredients of life. So, you see, the question of when and how Jupiter formed isn't just an academic puzzle. It's the key to understanding our own existence. Was Jupiter the gatekeeper that shaped the raw materials of the planets, or the delivery boy that brought life-giving water to Earth? The fuzzy core discovered by Juno leans towards a very early, very violent birth, which would favor the gatekeeper role, but the story is far from over. Future missions and more data from Juno will continue to peel back the layers of Jupiter's cloudy atmosphere, revealing more secrets about its core and its composition. By studying the isotopes' different flavors of elements within Jupiter, we can trace where its building blocks came from in the solar nebula. This will give us a definitive timeline and tell us whether Jupiter grew in place or migrated across the solar system. The story of Jupiter is the story of a giant that shaped its family. It's a cosmic detective story written in gravity and gas, and we are just now learning how to read it. What we find won't just tell us about a distant, stormy world. It will tell us about the chaotic, violent, and ultimately miraculous series of events that allowed a planet like Earth to form and life to flourish. The King of the Planets still holds the key to our own origin story. Thank you so much for joining me on this cosmic journey today. If you enjoyed this deep dive into the mysteries of our solar system, don't forget to hit that like button and subscribe for more adventures into the great unknown. Let me know in the comments which Jupiter origin theory you find most compelling. Until next time, keep looking up.